Hi, here for chapter 3. So I've really wanted to outline how all the things that we'll cover in this chapter first. So the first thing is going to be formula and molecular weights, and then percent composition of the formula, then empirical formula versus molecular formula. In fact, your lab this week is on the empirical formula. And we'll talk about Avogadro's number and mass, mole, and particle conversions. Then we'll do some balancing of equations and be able to write state symbols with the reaction. We'll talk about the different types of reactions. There's 4 that we'll cover right now. We'll cover more in our next chapter. And then we'll do some stoichiometry, and with stoichiometry, we'll talk about limiting reagents and excess reagents and percent yield. But that we're going to cover next week. So the first thing, formula weight, what is it? Well, we dealt with it some in our lab on gravimetric analysis. So what is the formula weight? It goes by a couple different names, either formula weight, molecular weight, or molar mass. Those names are used interchangeably. So if I have the molecule NO2, how do I figure out the molar mass of that compound? Well, I look at what I have here is the simplest whole numbered mole ratio of atoms. For every 1 mole of nitrogen atoms, there are 2 moles of oxygen atoms. And I'll talk more about that term mole in a few minutes. So first of all, I look up nitrogen on the periodic table. I have 1 of them represented in my formula. I multiply by the atomic mass of nitrogen, and then I look up the value for oxygen. I note that I have 2 of them in my formula, and I multiply by 16. I get those 2 values, I add them up, and I get my answer for the molar mass of nitrogen dioxide, 46.01 grams per mole. Grams per mole is the unit. Mole ends up being a counting unit that we use in chemistry. We'll talk more about it in a minute. So then there's another type that is a little bit more involved, something like barium nitrate. Again, I see barium. I have 1 mole of barium atoms represented. I look up the value for barium on the periodic table. And when I do this, I always go 2 places past the decimal point unless it's otherwise specifically required. So then I take nitrogen. There are 2 nitrogens. Now, how do I get 2 nitrogens in this one? So if there's a subscript outside of a parenthesis, you distribute it to everything inside the parenthesis. So I have 2 nitrogens multiplied by 14.01. And then because that 2 is outside the parenthesis, it goes for everything inside the parenthesis. So in this case, I actually have 6 oxygens. So then I would take 6 times 16. So I get those 3 values, I add them up. Now I have the molar mass of barium nitrate. Okay, so there's some examples of that to practice in the practice worksheet folder. I think that you did it during that lab on gravimetric analysis, so it's pretty straightforward, but definitely practice it. Then we're going to look at what is an empirical formula versus a molecular formula. An empirical formula, by definition, is the simplest whole numbered ratio of atoms in the compound. And then the molecular formula is the actual mole ratio of atoms. So sometimes your empirical or your simplest formula is your molecular formula, but not always. As in this case, the empirical formula is, the molecular formula is a multiple of 2 of this empirical formula. So in our lab that you're going to be doing this week, you're going to find what is the empirical formula when silver and oxygen are combined in a synthesis reaction. And you're going to end up forming silver oxide in this. But what you're going to be asked to find based on some quantitative analysis, what is that whole numbered ratio between the silver and the oxygen? And in the lab, what you're going to do is you're going to heat the silver oxide, and actually this reaction would be the opposite of this for the lab. But you're going to heat silver oxide, and it's going to release the oxygen, and based on mass differences, you're going to figure out what portion of the molecule is silver and what portion is oxygen, or what portion of the compound. So I just want to talk a little bit about, I'm going to go back to this equation because I don't want you to get confused, because the lab, I just wrote it the opposite of what it should be. So it's going to break up into silver and oxygen gas like that. But you're going to figure out what that X and Y would be. I mean, based on, your charges becoming your opposite subscript with the crisscross method that we learned during nomenclature, you could probably figure out what this ratio would be just by using that method. But you have to prove it quantitatively with the lab data that you're going to get from a video. Okay, so what's the mole? Would I talk about the mole? We've talked about it at other points, and so we've never really clarified what it is. So it's really a counting unit in chemistry, and it's used to describe a collection of very small particles, such as atoms. So we don't usually talk about one atom. They're too small. So we need a collection of atoms. So instead of just talking about one or two atoms of any particular element, we talk about the collection, the mole. Okay, so I'm going to jump down to this here. It's just like the unit, the dozen. So if I said to you, you have a dozen eggs, you would know that you have 12 eggs. If I said to you, you had a dozen atoms, you would say, or I would tell you that that's 12 atoms. So just like the dozen, the mole is just a counting unit. So if I have a mole of atoms, I have a specific value of atoms. It's huge. It's 6.02 times 10 to the 23rd atoms. If I had a mole of eggs, so again, it's just a counting unit. I can count anything, but a chemist counts small, tiny particles and uses the mole counting unit, because the dozen just isn't useful when you're counting very small particles. So if I have a mole of eggs, I have 6.02 times 10 to the 23rd eggs. As ridiculous as that may seem, not many farmers use the mole as a counting unit. So, up here, if I were to write this statement, 1 mole of calcium chloride molecules, I can use this mole term to describe anything. 1 mole of calcium chloride molecules. It's 6.02 times 10 to the 23rd molecules. If I have 1 mole of calcium positive 2 ions, I have 6.02 times 10 to the 23rd ions of calcium positive 2. If I have 2 moles of chloride ions, these are the components of this molecule, 2 moles of chloride ions. That means I have 1.202 times 10 to the 24th ions of chloride, because I'm going to take 2 times 6.02 times 10 to the 23rd, which will give me that 1.202 times 10 to the 24th. So knowing that we can use this counting unit to describe these tiny, tiny particles. Let's say that I have 0.25 moles of calcium ions. How many ions is that? Okay, or atoms, I could take it a step further. So I would say if I have 0.25 moles of calcium ions, I use this as my converter, or in my dimensional analysis, 6.02 times 10 to the 23rd ions or atoms per mole. And then what if I end up with, what if I go the other way? If I have this number, a very large number of calcium atoms, 2.60 times 10 to the 25th atoms. Well, I put what I'm starting with, my data point here, and then I use the 1 mole is equivalent to 6.02 times 10 to the 23rd atoms of calcium to make that conversion. I haven't finished the mathematics here, but I think you get the idea. So what if I wanted to convert 15 grams of calcium into moles? Well, then I would say if I take 15 grams and I use the molar mass now as the converter, I would just take 15 grams and divide by 40.08 grams to get the number of moles here. Then a different type of calculation, I could take, what if I have 15 grams of calcium, and my question is, how many atoms of calcium is that? Well, then the question goes a little bit further. I would start out with my 15 grams. I would use this conversion factor to get grams to moles. And then I would use this conversion factor to get moles to atoms. Because remember how we do dimensional analysis, the gram above the dividing line cancels the gram below. The mole above the dividing line cancels the mole below. And what do I have left? What's my only unit that I have left? It's atoms of calcium. So I'm going to take 15, divide by 40.08, and then I'm going to multiply by the 6.02 times 10 to the 23rd, and I would get my answer for atoms of calcium. And then what if I, went even a little bit further, and I said, all right, what if I had 55 grams of calcium chloride? And I said, how many molecules would that be? I'm going to start out my calculation the same way, but this time I'm not going to use just the atomic mass as I did here. I'm going to use the molar mass of calcium chloride. That's 1 calcium plus 2 chlorides added up. I get this 110. Then I'm going to say there's 6.02 times 10 to the 23rd molecules and 1 mole of calcium chloride. Again, there's that counting unit. And so I would stop my calculation right there if I was trying to find the number of molecules. But if I wanted to go further, I would just continue my picket fence for my dimensional analysis, and I could find out how many atoms or chloride ions there are, because what I know in my formula is that there are 2 moles of chloride for every 1 whole molecule of calcium chloride. So if I took everything that I did prior and I just multiplied by 2, because then molecules would cancel with molecules and I'd end up with the atoms or the ion of chloride and how many that would be. It would be a very large number if you calculated this out on your calculator. I'm going to stop there and I'll be back.